All right, now we're ready to look at some specific equations for oscillations of masses on springs and of pendulums. So in both of these cases, for masses and springs and pendulums, we can describe that behavior in terms of its frequency and or its period. And not surprisingly, the frequency and the period change when we change physical things about our system. So let's take a look at our mass on spring example. And I'm drawing this as vertical, but this works just as well if we have this horizontal. So maybe here's a surface, here's like a fixed wall with a spring, and this mass is like free to slide back and forth this way. There has to be no friction on this surface for it to work out nicely, but these two systems are going to exhibit the same oscillating behavior. So we're going to use these two models pretty much interchangeably in Physics 106. So whether the mass is oscillating up and down or side to side, it's not going to really affect any of the number calculations we're about to do. You'll have to trust me on that. But I'm going to drop vertical because I think it's a little easier to visualize, for me at least. Okay, so if we have a system that looks like this, we can change things about this system and they will change how our system oscillates. So for example, if we increase the mass here, and this is nice to do a demo of where you have a mass hanging from a spring and I can add more mass to it and we can see how the oscillation changes, but you'll have to trust me that if we add more mass, the oscillation slows down, meaning that it takes longer to undergo this oscillation. So that means there is a longer period. We can also have, with this spring, we can make this spring stiffer or softer by replacing it with a spring with a different spring constant. When we do that, we also change its oscillation. So if we replace this with a stiffer spring, one that gives us a bigger amount of force, it is able to accelerate this mass more easily because it is giving out more force. And as a result of that larger acceleration, the object moves faster. It takes it less time to oscillate. So higher spring constant, that is a stiffer spring, that actually gives us a shorter period. And if you happen to have springs and masses at home, you can totally play with this. But it's good to get your hands on this, but unfortunately we're not able to do that right now for this class. So for this system, I will just cut to the chase and write down the equation that you get for this behavior. So for the period of our mass and spring system, our period is equal to 2 pi times the square root of m over k, where m is our mass in kilograms and k is our spring constant in newtons per meter. That is the stiffness of the spring. So if we know values of k and m, we can plug them into this equation and calculate the period, calculate how long our system should take to undergo this oscillation. We also, since we know, F equals 1 over t, we can also write down an equation for the frequency of oscillation of this system. And that is just 1 over this equation. So that's 1 over 2 pi square root of k over m. So these are our two equations. I mean, we only ever need one of these as long as we know that this equation is also true. But these are the equations to describe the oscillation of a mass spring system. All right. We'll do an example in lecture later, video chat lecture, of plugging numbers in and calculating some actual periods and frequencies. But these equations are pretty straightforward to use. We're just plugging the numbers in. Okay. What about our pendulum equation? So we have our pendulum with a mass, and this string has some length L. So here, our period for the pendulum, that is the time it takes it to oscillate, swing from one side to the other and then back, like one full oscillation. Our period looks similar in some ways. It's 2 pi times the square root But now it is the square root of L over G. G is our good friend gravitational acceleration, 9.8 meters per second squared. L is the length of this string, or really, it's actually the length from the pivot to the center of the mass, if we're being careful, but usually in our problems, that's not going to make a difference. And the actual value of the mass does not appear in here. So in other words, if you have two pendulums that are the same length, and one of them has a marble and one of them has a bowling ball, as long as the lengths are the same, they're going to take the same amount of time to swing back and forth. So this is our pendulum equation. We can also write down the same thing for the, similarly to what we did for the mass and spring, we could write down the frequency version of this equation, which is just 1 over this equation, so 1 over 2 pi root G over L. All right, so for both the pendulum and the mass on the spring, we do know enough in Physics 106 to figure out where these come from. It's more time than I want to spend on it, and I don't think our book does it. And it's not something you have to worry about, but I don't want you guys to think that these are coming out of nowhere. These are coming out of some, F equals ma free body diagram kind of pictures. You can also get some pieces of this with by looking at some of the energy in the system, kinetic energy, and we'll talk more about the energy of these oscillating systems later on. Okay, but now we at least have some equations we can use to describe the motion of these oscillating systems. And next, we are going to start to look at graphs of how this motion looks over time, and also and what those graphs can teach us about what's happening in these systems.